Nick will tell us really about the fundamental concepts, the basics, and the units that are very, very key to understand with regards to storage, to make sure that we have all a common understanding of the most important topics, so that we can have very understandable and practical sessions later on today. So I am not going to make everybody wait any longer. I want to do a quick presentation about you, Nick, and then I hand over to you. Many of the listeners here today know of you, but for the few who might not yet have crossed paths, you're the VP of Huawei Digital Power for East Africa. You are bringing us today 15 years, even more than 15 years experience in renewables, in training, and also in logistics. I learned this recently. You've been working in Africa since 2006. So you know the location, you know the challenges, you know the solutions inside out. And previously, you've also been working with Jubilee Solar and Apex Logistics. So, Nick, I'm very, very pleased to welcome you once again. This is not the first time, and I thank you for accepting the invitation once again. It's always a pleasure to welcome you here, and I hand over to you now.
Okay, as John said, I am going to be giving you an introduction to some energy terms and basic sizing of the solar systems. All of this stuff is very foundational to the work we do in the solar industry. So I'd like to say thank you to John and the AFCIA team for extending this opportunity. And normally I do lots of presentations. This one is a new challenge for me because it's going back to the basics. So I hope it's not too technical. I am a visual learner myself, so I've tried to make this a bit visual and tried to show you how these terms are related to each other, because I know that helps me understand them. And as John mentioned, so here's a bit of the agenda. We'll talk about amps, volts, watts, kilowatts, watt hours. We'll have a brief look at some power curves, because I think that helps understand these terms. And then we'll have a brief look at load profiles and how it's related to these terms and how it's related to solar energy. And as John mentioned, my name is Nick Lusson. I'm the Vice President of Huawei Digital Power for Eastern Africa region. So if you need anything or need more information, feel free to connect on LinkedIn and get in touch after the presentation. So to start, we need to understand voltage and current and power. And so it's written on the screen there. Voltage is referred to by the letter V, and it's measured in volts. Current is referred to by the letter I, and it's measured in amps. And amps is referred to with the letter A. Power is P, and it's measured in watts. Watts is the letter W. So I know this can be a little bit confusing because voltage is always the letter V, but current can be I or A, power can be P or W. So this is just something you're going to have to memorize. And there you can see in the center of the screen the formula of how they are related. Current times voltage equals power. This is also I times V equals P, and amperes times volts equals watts. So this is something that I think you just have to get very familiar with: voltage, current, and power. And when you have 1,000 watts, you get a kilowatt. And then the next level is to add the hours, because if you use 1 watt for 1 hour, that is a watt hour. And if you use 1 kilowatt for 1 hour, that is a kilowatt hour. So kilowatts, watts and kilowatts, we're talking about the inverter capacity. Inverters are measured or rated by their kilowatts. And then batteries are measured and rated by watt hours or kilowatt hours. So this is a common mistake that people make, that the batteries, they might say, I have a 5 kilowatt battery, and that's not technically correct. Batteries are measured with watt hours. So you could have a 5 kilowatt hour battery. And the same is true for the inverter. You cannot have a 5 kilowatt hour inverter. The inverter is kilowatts and the battery is kilowatt hours. So I'm just going to repeat myself because I think that's very important for learning. So, and this part, this is just kind of pure memorization. You just have to remember these terms and where they go. And then the next part, I'll show you some visuals, how they're related. But voltage is V, and it's measured in the unit of volts, which is also V. So you can say you have 10 volts or 100 volts. Current is the letter I, and it's measured in amps, which is the letter A. So when you're talking about current, you could say I have 10 amps of current or 10 amperes of current. And power is P, and it's measured in watts, which is W. So you can say I have 10 watts of power. And then when you're using power over time, that's how you get like the watt hours. So by the way, in the metric system, I think we all know that when you have 1,000 of something, it becomes a kilo of that. So kilowatt, kilovolt, kiloamp is 1,000 of them. And when you use a watt for 1 hour, it's a watt hour. When you use a kilowatt for 1 hour, it's a kilowatt hour. And inverters are kilowatts. Batteries are kilowatt hours. All right. So this, as I've said, this part is pure memorization. You just have to get comfortable with it. But now we can try to put it into a visual context or see how they're related. So one way that is useful to remember this stuff is if you compare the electricity to water. Okay, because I think water we're more familiar with, so we can kind of use that as an analogy. So the battery capacity is like your water tank. The battery capacity is your water tank, and how much water is in there is like how much charge you have. So for example, if we add some charge, now we have more water, but the kilowatt hours is the battery, and that you can imagine it like a water tank, because we're talking about how much capacity can you hold. Okay. Now, the inverter is something like the pipe that would be going in and out of the water tank. That is the kilowatts. All right. And that's the inverter. The analogy is the inverter is the pipe. So what I want you to realize is that if you had this water tank and you have the capacity, then you have this pipe that comes out of it. You could never get more water out of the tank than the size of the pipe. Okay? And that's the same with the inverter and the battery, because you could have lots of battery storage, like 15 kilowatt hours of battery storage. And your inverter might be much smaller, only 2 kilowatts. That means at any one time, any one particular time, you could never get more than 2 kilowatts. If we increase the pipe, now this is a 5 kilowatt pipe. Now, at any one particular time, we could get up to 5 kilowatts. Not more, but definitely less. So that is the image I want to show you to help you understand this. The water tank is the kilowatt hours. It's the battery. Kilowatt hours is battery. It's like the water tank. And kilowatts is the inverter. It's like the size of the pipe, because this means you could never get more than 5 kilowatts at any one particular time. Just like the pipe, just like the inverter. All right. I hope that analogy makes sense. And then let's say if you use this pipe at its full capacity for 1 hour, that means you have consumed 5 kilowatt hours, right? So then here, right here, we have 10 kilowatt hours of storage. That means we're going to use half of this in 1 hour if we consume 5 kilowatt hours. And for example, here, if we use this pipe at the full capacity for 1 hour, that means it's 2 kilowatt hours. So the inverter is like the size of the pipe, and it's the maximum that we can get at any particular time. And when we use that for an hour, then we get the kilowatt hours. And then in this analogy, the voltage would be the pressure, the water pressure. How fast is that water going to shoot out of the pipe in a way? And then the current is the amount of water. So it's not a perfect analogy. It doesn't work exactly 100%, but I think this is a useful analogy to help you understand these terms and how they're related to each other and how they're related to solar energy. Now, I want to take you to another visual, which will be the power curves. Because this is called a power curve. And we have the current on the vertical axis and the voltage on the horizontal axis. And the reason this is useful to know, and it helps you understand these concepts, is because when you multiply the current and the voltage, you get the power. So what I mean is, if this line, by the way, this line is very common on solar panels. Every solar panel has this type of power curve, okay? That's why it's useful to us. And what I want you to see, that if we're operating at this point here, it's 9.8 amps and 10 volts. This blue rectangle represents the power, because we do 9.8 amps times 10 volts, 98 watts. And if we change that, now it's 9.4 amps and 11 volts, and this is the power. So as you change the voltage and the current, you're changing the power, because the power is the voltage times the current. Okay, so that's what this visually shows you. The voltage times the current gives you the power. And as you increase the voltage, you typically you're decreasing the current. And I hope you can see that. So we're moving along this power curve. See right here, 18.8 volts, 4.8 amperes, 90.24 watts. And if we go back the other way, 18.5 volts, 5.3 amperes. So this is how they are related. The voltage and the current determine the amount of power. So I'm just going to go back and forth a few times so that we can get this concept. Current is the amperes. It's the letter I, and it's also the letter A. Voltage is the letter V. Here we can see I times V equals P. The current times the voltage gives you the power, which is watts. So this curve is something that's typical of a solar panel. If you have the maximum current up here with the 0 voltage, this is a short circuit. This is what happens when there's a short circuit. The voltage goes to 0 and the current goes to the maximum. So on the solar panel, this is also on the data sheet. This number up here is ISC, the current for the short circuit. So again, guys, I'm trying to give you too much information so that you can see how it's all related. If this is new to you, don't feel bad if you don't remember everything and don't get everything that I'm saying. Just try to get the basics. I'm trying to show you the relationship here. Current times voltage equals power. And what a solar panel is capable of is this curve. And as you increase the voltage, you have to decrease the current. But you're changing the power. And what you can notice is that this blue rectangle, which represents the power, it's changing in size, right? And the number here, this watts, is changing. That means there is a point on this curve that will give you the maximum power. Here's 135. Okay, here's 153. That's a lot. But then we go back down to 128, 103.4. So there's a maximum power point here. Right about there, that's when you get the most power. When you use like 17 volts, 9 amperes in this example. So when you hear of MPPT, the maximum power point tracker, this is exactly what it is doing. It is using this curve. This curve is determined by the panel. And the MPPT is trying to always find the balance that will give you the most watts. Because when you change the current and the voltage, you're changing the watts. So that is the important relationship I want you to understand here. The current times the voltage gives you the watts. And when we look at a solar panel, the solar panel has limitations. So we want to find that point that gives us the most power. That's an MPPT. Okay, so I think we can continue. So that would be the maximum power point. You see that blue rectangle is the largest when you have the peak of the maximum power point. You balance the current and the voltage precisely. Now I want to show you something called a load profile, because this is very important in the solar industry and it's related to this. Now, what I'm showing you is now kilowatt hours of consumption. So it's no longer, we're not talking about voltage and current anymore. Here at the bottom is the time of day. Okay? And here, the vertical axis is kilowatts. So what this graph is showing you, this is typical of like a business. Because this means at 6 a.m., they are not consuming a lot of electricity, but then around 7 a.m., their kilowatts increases because they're switching on all their machines. And through the day, it goes up and down, maybe a little bit of a dip at lunchtime, up and down. And then around 5 p.m., they start to switch off the machines and go home. Their power consumption drops. Nighttime is probably like security lights and things like that. So this is a load profile. The previous one we looked at was a power curve. This is a load profile. And it has hours of the day at the bottom, and it has kilowatts on the side. So this is showing us kilowatt hours of consumption. So here, this is what we call the base load. So this means basically it's the bottom. It's how low they go at night, the base load. And this up here would be the peak load or peak demand. So in this example, their peak is just above 250 kilowatts. So once again, I hope I'm not overwhelming you. I'm trying to go slow, but I'm also trying to introduce you to the important concepts and relationships. Now, there's one other curve that you should really know. This is the solar curve. Now, what this is showing you is the amount of solar energy that is available throughout the day. Here at 5 a.m., there's not a lot because the sun is just rising. Then as the morning progresses, the solar energy increases. And around lunchtime, this is when there's the most solar energy available. And then it begins to decrease in the afternoon and the evening. So this is the solar energy available. This here is the hours of the day. Okay? And I want you to notice something. I haven't put any numbers here on the left. That's because this number will be determined by the equipment. This curve does not change. Every day, this is like this. And everywhere across the globe, it's like this. So this number here would be the kilowatts. It's determined by your equipment. So if you install 200 kilowatts of PV panels, that's the peak number here. Your panels will produce their rating at the peak time only. So if you have 200 kilowatts of panels in the morning, you're not getting 200 kilowatts of production. Only at the peak will you get the 200 kilowatts. So now, what's very important is to combine these two load profiles. What I mean is like this. So when a customer says they want solar energy, we start with their load profile, which is the red. We need to know how much kilowatts and how much kilowatt hours they are consuming. And then we need to know through the time of day, and we can match it to the solar profile. Now, this example on the screen has no batteries. This is grid-tied solar. And the components you would need are the panels and the inverter and maybe other accessories. That's all. There's no batteries on this one. But then what happens here is when there is a grid blackout, even the solar will stop producing. So that is a challenge. So that is a big reason why people need batteries, especially if the grid is unreliable. Because in this scenario, when the grid fails, even the solar fails as well. So when a common solution is to use diesel generator as a backup. And once again, guys, I'm doing this visual exercise with you so that you can help understand how it's all related. You don't have to grasp everything right now. I'm just trying to show you how everything is related and visually. So if they have a diesel generator, when there's a blackout, if you can see previously they had no power and now they're using diesel generator. But what you'll notice is that there's this small gap. That's the startup time. So maybe we've all experienced this when there's a blackout and the power goes off for a few seconds and then the diesel generator comes on. That's what you're looking at right now. The way to avoid this is if you keep the diesel generator running all the time. If you keep the diesel generator running throughout the day, you don't have that small gap. But of course, you are consuming a lot of diesel. So what you can do is you can use batteries. So here in the green color, there's a grid blackout, but your batteries are kicking in. But what that means is you have to charge the batteries with the grid because right now there's no solar energy. So your grid bill will go up because you'll be charging the batteries at night and you'll be consuming the batteries when there's a blackout. But what you can do, so in this situation, the components would be the battery, the component would just be a battery. There's no solar in this example. And this is what some people do for battery backup. You just get a battery and it charges from the grid. But what you can do is, if we look at the solar profile, we can use the solar energy to charge the battery. And I want you to notice we're charging at the peak time. That solar curve has not changed, but we can add more panels and we produce excess power and we charge the battery. And then the battery can supply the power even when there's no sun, even at nighttime, even in the morning, even in the evening. So in this scenario, the components would be these. You still need the solar panels, you need the inverter, and you need the battery. And now we're at the end of this presentation, but just to tie it together, the solar panels, their sizing is in watts or kilowatts. The same as the inverter. The inverter is kilowatts. And the battery is kilowatt hours. The watts, when we talk of the panels and the inverter, I've said they're measured in kilowatts. That comes from the voltage and the current. The voltage times the current gives you the kilowatts. So they're all related. And when you use a kilowatt for 1 hour, it's a kilowatt hour, and that's the battery. So I hope this has been helpful, and I hope some of the images will stick in your brain and help you understand this. Especially the water tank one has really helped me. The battery is the water tank and it's kilowatt hours. The pipe is the inverter and it's kilowatts. And if you use watts for an hour, it becomes kilowatt hours. So thank you very much for your time. I think now we might have an opportunity to go into some questions.
Yes, Nick, thank you so much. You're a little bit in the dark there, but your presentation has been truly amazing. There were so many comments about how great your visuals were, how crystal clear your explanation was, and really thank you very much, because I think this was an essential building block to get this entire week of conference started. Really helpful. Thank you so much. I want to jump right in some questions that we have received. You did some really great visuals about the importance of load profile and how we can use this to determine what storage is really needed for a specific customer. We will talk about this more in detail in a session later today. But Yusuf is wondering, like, how do you get the load profile of a customer, and especially of a residential customer, because rarely do they keep charts and graphs of their load consumptions.
Yes, that is a good question. So the normal way to get a load profile is with a device called a data logger. And it's a piece of equipment that many solar installers have. It's very important. And typically the solar installer will go to the site and install their power logger and leave it for 7 days. And then after 7 days, they come back and they see the data, because this data logger will measure that load profile every minute. And you leave it for 7 days, 24 hours, and then you get that data. Now for residential, it's a bit less important, to be honest, because you can estimate usually pretty well. So typically the data logger is for businesses, and at home you can still do that and you'll get very accurate information. But what's more common at home is you do estimates based on what the homeowner tells you. So for example, they would tell you, I have a television, and the television has a rating of how many watts. Let's say it's 80 watts. And you ask the customer, how many hours a day do you watch the television? And they might say 2 hours a day. That means that will require 80 watts times 2 hours, that's 160 watt hours. And you have to do this with all of their devices, every light, their refrigerator, everything. And if you do this, you can get a good estimate, and you probably know. And by the way, most homes are quite similar, right? I mean, there's some differences in family size, but you get to know, okay, this person needs a 5 kilowatt hour battery with a 3 kilowatt inverter, or this is a bigger family. They need a 10 kilowatt hour battery with a 5 kilowatt inverter. So to answer your question, you can use a data logger, and this is the correct procedure for businesses. For residential, you can estimate and you can kind of get an idea if they are small family, big family, medium family, and you can get a good estimate of the size they need.
Thank you very much, Nick. Next question from Ibrahim. Why would grid-connected solar stop producing during a blackout? Can it not be isolated for local use? You're on mute, Nick.
All right, thanks. So that's another very good question. And this answer is a little bit technical, and it has to do with the voltage and the frequency from the national grid. Because the national grid operates at a certain voltage and frequency. Normally, this would be the voltage on a three-phase would be like 415 volts. On a single phase, it's like 220 volts. And the frequency is hertz. It could be 50 hertz. Now, the grid, the national grid, fluctuates a little bit. It's not always perfect. It goes up and down. But it's very important that everything that's connected to the national grid follows the national grid. If the voltage goes up, it must go up, and the frequency too. So, to answer your question, if there's a blackout, why does the solar energy go off? It's because the solar energy must follow the national grid with the voltage and frequency. It's called a grid reference. So when there is no grid reference, the inverter doesn't know what to do. If it operates at its own voltage and frequency, and then the grid comes back, it will damage the inverter and cause problems on the grid. So I hope that's not too technical. I hope I answered you a little bit. It's for the grid reference, because the inverters need to know the voltage and frequency that they need to operate. If you have batteries, the batteries can provide the grid reference. So the batteries allow it to stay on. But if you don't have batteries, most of the time, when the grid fails, your solar energy will go off as well, unless you have a diesel generator or batteries to provide the grid reference.
Thank you very much. And there's nothing too technical, no worries. This is why we're here. And maybe we'll take a last question, because I see Muisa has joined us. Hello, Muisa, welcome. You'll be up in just a few moments. We'll take one last question for Nick. Question from Otuo. Can you differentiate between the PCS and the inverter?
Yes, sure. So a PCS is a power conversion system. And it's a name of a device, just like inverter has a meaning about what it does. A PCS is a term that it means something. And what it means, it's basically a bidirectional inverter. So an inverter accepts DC power and changes it to AC. That is what an inverter does. All inverters do this. If it doesn't do this, it's not an inverter. And then a rectifier is the opposite. A rectifier takes AC power and converts it to DC. A PCS does both of these things. A PCS can go from AC to DC and DC to AC. So if this is necessary, it depends on your equipment. And I included it because I work for Huawei, and with our CNI batteries, it's required. And generally, all batteries are DC. Basically, all batteries are DC. and all solar panels are DC. But all of our loads are AC. So you need the right combination of PCS and inverter to get the DC when you need it and the AC when you need it. And then the PCS, for example, it accepts AC power and then DC for the batteries and then back to AC for the load. So a PCS is a bidirectional inverter. It can go AC to DC and DC to AC.
Wonderful, Nick. Well, thank you so much.